Thank you, Pat Dewey. And thank you to Wicca for the opportunity to speak here today. Okay. So the construction industry has enjoyed relatively little growth in productivity over quite a few many generations, as you know. And it's among the least digitised industries in the world. Now, New Zealand has a BIM acceleration committee, and what they've said of BIM in construction is, of all the improvement initiatives investigated, BIM is the only one which holds the promise of a step change in productivity rather than just an incremental change. So it's quite a difference. Now, BIM, as you know, offers opportunities through all stages of a development's life cycle, from the beginning of design through construction and into operation and maintenance. But with few exceptions around the world, the progress in take-up of BIM is actually relatively slow. In Indonesia, it's also slow. Part of the reason for that is that BIM systems like Revit are seen as having limited advantages over CAD in the industry. They see that Revit's really just a new 3D type of drafting software with new costs in training of staff and licensing of the software. Now, we do see Revit increasingly being used by contractors like Wicca, doing final coordination, construction planning, seeking clash detection, but this is all after design's complete. The opportunities and scope for BIM to offer advantages to a project are obviously much greater than this. Now, TTW, we've been using Revit for all of our drafting here in Indonesia for over 2 years. In Australia, we've been using it for more than 12 years. In this presentation, TTW, I'll show for you some of the BIM innovations that we've been using in design, in the design and documentation stages of projects. So these examples will show how engineers, contractors and other designers can deliver better cost, time and quality value to all their projects, especially in terms of more efficient designs, but also providing better buildability to complex designs. So I'll present some structural engineering problems on behalf of TTW, and Matthew will then present some MEP types of solutions on behalf of Floth. So computational design methods are about solving structural engineering types of design problems simultaneously with other non-structural engineering criteria, which could be buildability criteria for a contractor. They could be MEP or soil engineering related criteria. All types of things that go into decisions in a design process can all be optimised quite well using BIM and related technologies. So traditionally in a design process, you'd have the design team sitting around the table. We'd identify critical criteria for our own disciplines. We'd maybe select 4 or 5 different scenarios that you'd go away and study. And so everyone does their study. You come back, compare the results and decide together on which one's the best one. Now, using computational design methods, it's possible to consider thousands of possibilities in potentially less time and thereby achieve much better optimised solutions. So I'll now present to you 2 examples. The first one is an improved workflow type problem in producing rebar shop drawings for a project, and the second example will be one where we optimise a complex geometric roof shape to provide buildability. So yeah, the first example is in regard to automated production of rebar shop drawings. So the project is Coffs Harbour Hospital in New South Wales in Australia. On the left you can see an image of the partly completed project, and on the right we've got a structural engineering, an image of the structure Revit model. We've actually got integrated Revit models for this project with MEP and architecture as well, but that's not what I'm showing you here today. So this project has hundreds of different columns. The contractor was a design and construct contract. The contractor's decided that he would like to precast the columns, and he's decided this, you know, within a month of actually wanting to commence that. Design actually was not complete. The whole design team was still working on the project. So clearly there's a problem in terms of how to get this precasting underway. So what we did was we created a script to streamline the production of those shop drawings for the precasting process. With the aim of producing a drawing like this. And what you can see on here is there's a whole lot of information that is part of the normal structural engineering design process, but there's a lot of information on that which would also be provided by the builder. So our goals were to provide a single end-to-end delivery process. So taking it from design right through to the completion of the fully detailed shop drawings in one step. We wanted to obviously achieve a high quality design, cost effective, in a short time, and with no design defects. So we did this by scripting that workflow in Grasshopper to combine the engineering and drafting software and other specific criteria in there as well. So this is a quick demonstration of the actual workflow. So it takes the geometry from Revit into the analysis software, in this case ETABS, puts those results into the design post process, or in this case an internal TTW program, takes those results back out, puts them back into Revit. A key point that I'd like to make here though is that while, for example, ETABS and its post processes can carry out all of that design in one step itself, ETABS does not give you all of the detail you need to actually build the structure. It doesn't tell you things like, well, in the case of precasting, grout tubes and ferrules and things to go in there. It doesn't give you position of bends. It doesn't give you other special detailing requirements which may be required in the code. Revit also has things in that which enable, which help enable automation of this drawing production process. But Revit doesn't actually know the specifics of your project. There are still decisions which need to be made and put onto the drawings by an engineer and a drafter. So this type of workflow process actually takes care of all that in one step. So this is just quickly demonstrating the steps for you. So step number one, we're actually loading up the geometry into ETABS and bringing in the load combinations there from a CSV file. We then put all of that into ETABS and run it. Take those results and put them into the design post processor. We've then got a manual part of the process which is checking and validating that design. Then we export those results to Revit, create the actual information that needs to go on the shop drawings, and then generate the shop drawings. So I'll now show you 3 quick animations that actually demonstrate that process. This first one's just generating the results of the analysis. So the program automatically opens an instance of ETABS. It pulls in all of the ETABS bar elements, filters that set of elements. We want the columns and not the beams out of the bar elements set. The results are then passed to the column design software, which carried out around 30,000 individual design events. The results are then written into an XML file for use by the next part, and it'll just give a quick visualization of those results in Rhino. The next animation shows the automated production of the rebar. So it starts with the contents of the XML file. Now in Revit, the file is then loaded by a custom plugin. Some options are chosen about what specifically to import. So we select columns, you know, whether we want precast or in situ. In this case, it's precast. And other details like grout tubes and ferrules. Now the add-in creates a new 3D window with all of those imported members, and we can show the reinforcement within translucent columns. So the third animation shows actually generating the shop drawings from that information. So the bars from the previous animation there are shown. Now some custom Dynamo scripts in Revit automatically group the columns and reinforcement into what Revit calls assemblies. Into the assemblies. And those assemblies automatically create the views and schedules. Now the script generates drawing sheets and places the views and schedules in a predetermined layout. And the end of the video will show the creation of the first 50 drawing sheets. And this is the end result. So you can see there's a lot more detail on these drawing sheets. There are around 300 of those produced and was able to be done in a relatively short time frame. Yeah, so just summarising again quickly, analysis through the design, documentation and fabrication. So I'll show you a different type of design example now where we're taking a complex roof shape and we're going to produce a buildable, typical type of design out of that. So the building's Department of Lands building in Sydney. You can see a street view of the building there on the left, and on the right we've got some views of the roof space. Now the object of the architect using these double glazed panels was to provide obviously a roof space which could be used in all types of weather, all seasons. So our goals for this exercise were to achieve the architectural form, visual aesthetic, to design a safe and serviceable structure obviously, but also to rationalise that structure and its geometry for fabrication and construction. So these diagrams describe the plan outlines and other parameters of the design. On the left in the red, you can see the shape of the different roof enclosures on the corners of the building. On the right, we've got a single line that just defines the surface geometry. This elevation shows the brief that we were given, which was basically that the architect wanted the roof panelised into diamond type shapes with the first node around eye level. So initially we looked at a number of ways to discretise this. Now we started with what's called a relaxation technique, and what that involves is placing the structural elements on the surface, and you then apply a set of forces into that to try and see how that structure wants to relax into shape. So the set of forces that we applied in this case was to reduce the length of all members by 5 or 10%. So you can see that on the top left, and then below that you can see the type of shape that that relaxation method then adopted. Now the success criteria for that are obviously that the members need to remain more or less on that surface within a strength-like set of criteria. Now the resulting curves there obviously involve an inherent twist as a member moves around that surface. That creates difficulties for construction, obviously. So what we looked at doing, as you can see on the top right there, is you can see that we've introduced step changes in the rotation of these members at the nodes. Unfortunately, that means that all of these nodes are then unique, so it's still not terribly buildable. So we've got a solution that's starting to work structurally, but it's still not a buildable solution. So we started looking at ways to define this surface mathematically. Now, the shape of the roof was actually close to a circular arc, so we agreed with the architect to make it an actual true circular arc. We then looked at ways to define these beam shapes mathematically using geodesics. Now, geodesics are a straight line in space, and solving these and defining these is often a complex computational type of problem, but in the case of a cylinder, which we've got a segment of here, a straight line wrapping around a cylinder is called a helix. So the equations you can see there are the equations of the helical beam lines running around the surface of the roof.
I'm sorry, Marten. Can you make it faster? Time is up. Thank you.
So this just to show you the buildability of this, what we've got here is just running the relaxation technique. So different colours represent different panel types. So we can see here, just based on the relaxation technique, we end up with actually over 290 different panel types, not a terribly buildable solution. Now, using the mathematical definition approach, again, different colour represents a different type of panel. We've ended up here with 244 panels being identical. Most of the panels come in around 270 or so types of panel. There were 29 types of panel in all, so still ideally you'd like to optimise that a little bit further for construction, but you've got a solution there that can be built, and many of the other panels are actually mirror images of each other. And you can see other benefits. The nodes become typical, which makes it possible to cast those. The beams on identical panels are also identical, so it becomes a buildable solution. And you can see an image of one of the cast nodes there in the middle at the bottom. So that's just what the node looks like. I'll skip forwards and pass you over to Matthew for some MEP demonstrations.
Thank you. Thank you. Thank you for allowing me to speak tonight. My name is Matthew Boynton. I work for Floth. They're a services consulting company based in Australia. I'm a BIM manager, and we've had a presence in Indonesia for 28 years. These are some of the services that we provide, and this is an overview of what I'll be talking about today. The central theme of my talk will be connectivity. So I think that this is a fundamental aspect of BIM and digitalization. Looking at processes and making sure that if you've got a complicated or too many steps in your process, is there a way that we can streamline these processes? And also about, I'll be talking about connecting teams together, so enabling better collaboration, better coordination, and better communication. So a good representation of the evolution of BIM for us is these lift documentation. So 10 years ago, the process would have been that we would receive, or the engineer would provide a hand-drawn markup of some other lift where they'd crossed out all of the dimensions, and then it was for the drafter to carefully select all of the aspects of the lift and stretch it out in AutoCAD. And it was a very, very manual process. It seems to have frozen. A very manual process. It was all very disconnected. You had to do it in multiple locations, so mistakes were inevitable. and there would often be a number of revisions, and it would take a very long time to make these changes. So it made sense, if I can jump forward, it made sense to go into the 3D environment. Seems to be frozen. Oh, there we are. Here we go. Okay, sorry. So when we moved into Revit, it meant that we could, we had this 3D parametric representation of the lift, which meant that we could make changes all from one place. And that improved not only our documentation, but it meant that we can make a change in one place in the drawing and it would automatically make that change throughout the drawing and the model. So that improved our time, it was drastically reduced our hours, and we made much less mistakes, but it was still the same process of a hand-drawn markup given to the drafter, and they just had to manually input that data into the model. So later on, we refined our techniques. We started using some traffic simulation software to get our data, which went into a spreadsheet, and that spreadsheet acted as a single source of truth that we could simply point our model to and pull that information directly into that model. And the benefit of that is that if we needed to make a change in the model, all we had to do was modify the spreadsheet, and that change would automatically update in the model. So we could, our drawing times or our modeling times were reduced from maybe a day down to only an hour, and it was not uncommon to get it right the first time, so there was no revisions. And then moving to the present, we're no longer just creating these models to make our drawings, because the model acts as a data-rich source of information that we can just extract the information from. So now we're looking at new ways to present that information to people. So we're looking at things like AR, VR, and gamification. So you can imagine this is a university, and you need to find your way around. You can find out from the model what's the shortest route to where you need to go. It'll tell you what distance you have to travel, the time it's going to take, just like Google Maps. And we can do all sorts of other things. So imagine in the model, we adjust the lighting, and in reality, that lighting might actually dim or change color. It can be used for training purposes. We can show emergency exit procedures, and we can use it for CCTV analysis. So that's useful for if we need to check that that we haven't got any obstructions to our visibility. But also, you could imagine in the future, you could click on a CCTV camera and get a live feed from the real world. So you're only limited by your imagination as to what you can do with the model. So I'll just kind of quickly, it's important for a BIM manager to look at our tool ecologies. So here we're taking our Revit model, passing it into SketchUp, it gets processed a little bit, we apply our materials in there, and then we get our schedule information, load data, weather data gets put into Open Studios, which will go into Energy Plus and give us our results. So pretty similar story for how we get our radiance. Again, we start with our Revit model. That goes into Rhino, we process it in there, look at the materials, I'll skip ahead. And then in Grasshopper, we take all the information we need, and we get this nice color scheme of our floor plans that we can use for, and sometimes it gets fed back into Revit. Schematics are an important tool for engineers in the MEP because they can show us, well, we use them to find out, or make sure that our systems are balanced. And we haven't undersized or oversized the pipework or the ductwork. So these smart schematics, thanks to BIM, the disconnect, or there's less of a disconnect between the calculations and the drawings. So all we have to do is connect up the system, and it will automatically, all of the flow calculations are calculated throughout the whole system. So we can use this to simulate all sorts of things, like if we have to replace or maintain equipment, we want to look at the operation during different times of the year or different times of the day. So yeah, it's useful to have a good schematic like that. Another benefit of BIM, apart from the fact that it's a nice way of visualizing the data with colors, is that when you place an element in a space, it automatically recognizes the location data, and we can harness that information. We can use that, we can take advantage of it by, in this case, we're looking at a particular room type and changing the flows everywhere where that air terminal is in the room type, just in the schematic. And that will automatically update the ductwork, which we can automatically size. And then we can use that information to pass to the architect so that they can size their risers. Well, moving forward. Because we work in we're now using marking up in a digital environment in PDFs. We can take that digital information, extract it from the PDF, and put it directly into, or transfer it into Revit using algorithms. We can take things like not just the location, the level, we can take the functional data and push it in automatically. And the same algorithm can pretty much be applied to making sprinkler layouts, light layouts, diffusers, flows, and other things. It's quite important for us to calculate the equipment's static pressure calcs, which is a pretty tedious job to do, especially if you're doing it by hand. And we've got so many systems in a building. If you don't get do accurate calculations, it can mean that either the fan or the pump is, it can't deliver, it can't operate, it can't deliver the water or air to where it's got to go. It can also mean that it's a noisy system, and it can have a cost effect for the operations of it. So Revit has the capacity to calculate the pressure losses in a system. However, the report that it gives it's a lot of data. It's really too much information for someone to look at, and it's got a lot of unreliable information too. So looking at that data, the grey stuff is stuff that we don't need. It's not really important. The yellow stuff is unreliable, and the green stuff is the good information that we can use. So what we do, we take the report from Revit, we take the good information from it, the green stuff, and then we place it we combine it with the good information from Revit using a complicated algorithm. And that means we can just run it and we can get reliable, fast information quickly, and we can apply it to all the systems in the building. And it's fast, quick, it's good, it's everything you want. So we just paste it in here, have a nice report, there's our result at the end. So if we have early contractor engagement, it can be beneficial to the outcomes of the building process. Because in this example, I'm kind of rationalizing and optimizing our duct layouts, which is ordinarily a job for the contractor to do. But we can kind of consider what their preferences are, such as standard duct lengths that they would use, so that we can automatically convert it to fabrication parts more easily. So that, I guess the end goal is that our design documentation is not so vastly different from the contractor's documentation. It's just running an algorithm. And we can also look at the cost benefit of doing that exercise. How much are we going to save by optimizing these ductwork just in material costs, not even considering the the labor costs of having to perform that exercise later on in the project. So just skip ahead, we kind of just add up the money. So that's kind of just an overlay of the original with the optimized design. And of course with BIM, it's really good to get some analytics out of it and have a look at these costs. I apologize, it's in Australian currency. I kind of did the conversion. It's sort of looking at about 30 million rupiah. And it was a typical floor, so we can actually multiply that by 10, so $300 million worth of savings, potentially, in only a few hours work, or maybe an hour's work. So it's just also fun to just click on the data and see what it does. See where the major cost benefits are. So now that we're moving to cloud-based collaboration, it means that we can exchange models more frequently, which comes with challenges as well. In particular, the major one is knowing what's changed between versions. So thanks to these comparison tools like BIM 360, it makes it a lot more transparent, it makes it a lot more easy to figure out what's changed between models, which kind of means that you don't have to rely on people providing descriptions of what's changed, because you can visually see exactly what's been modified each time you get the model, and you don't have to rely on people's opinion, oh, we didn't make any changes between this model, or they say they have made changes, but they actually haven't, so it's keeping people honest. Lastly, I just want to talk about cloud-based coordination. Oh, don't skip. No, go back. Oh, sorry. That's not the end. One last video. Sorry. Okay, should play now. This is it's kind of like a common data environment. I really hope the video plays. What you've seen earlier today, bringing all the information together. Is there a way that I can make this play? Oh, yeah. Not going to get the play. It's all right. But it's what you've heard before. That tool is used to bring all the federated models. It can take IFC. You can take point clouds, photographic mesh data, and the main thing is it's for coordination, which you all know it's not just about clash detection, which it also does very well. It's also well, the main thing that we're trying to do is to if there's some of the team members are not supplying the information that we need that's going to hold up the project, then we will be we're flagging that issue and prioritizing it and making sure that the project gets delivered on time. I apologize for that little thing. I might just cut it there. Thank you very much.
First, for Matthew.